Welcome back to Basic Electronics. We have seen how to design a synchronous counter to satisfy the given state transition table. In this session, we will follow that procedure to design a counter. We will also simulate the counter and verify that it does indeed follow the state transition table we started with. Okay, let us get started. Let us consider this design problem. Design a synchronous counter with the transition table shown in the figure and verify your design with simulation. So here is the transition table. We have Q3, Q2, Q1, Q0 equal to 0, 0, 0, 0 in the first state, then 0, 0, 1, 1, 0, 1, 1, 0, etc. And after 9 states, we are back to 0, 0, 0, 0. So it's a mod 9 counter. And this is how the counter can be implemented. We have 4 flip-flops here. The outputs are Q3, Q2, Q1, Q0. Our first job is to design this counter. That means we need to figure out what J0 should be, what K0 should be, what J1 should be, etc. in terms of Q0, Q1, Q2, Q3, so that the counter follows this transition table. And our next job is to simulate this counter and make sure that it does indeed follow this transition table. So let us begin with our design process. This is the transition table that the counter must follow, and here is a table that we have seen earlier which can be used in the design. If we know Qn and Qn plus 1, this table tells us what J and K should be. And note that we have the positive edge of the clock indicated here because we're going to use positive edge triggered JK flip-flops. What we need to do next is to obtain Carnot maps for all of these J0, K0, J1, K1 and so on based on the transition table that the counter must follow. Alright, let us begin with the don't care conditions. That means the conditions which are not listed among these states, and those can be marked right away as excess. For example, this state Q3, Q2 equal to 0, 1, Q1, Q0 equal to 0, 1, that is 0, 1, 0, 1 is not listed in the transition table, and therefore we don't care whether that is 0 or 1. So therefore it is marked as X. Okay, now let us consider the first state, that means 0, 0, 0, 0. Now after the clock edge, the active clock edge, our Q3 must go from 0 to 0, Q2 must go from 0 to 0, Q1 must go from 0 to 1, and Q0 must also go from 0 to 1. So let us look up the required J and K values for this transition 0 to 0. That brings us here, and that gives us J equal to 0, K equal to X. So for a J3 and K3, we must have J equal to 0 and K equal to X. And the same thing is true also about J2 and K2 because Q2 also goes to the same transition. What about Q1? Q1 goes from 0 to 1. So let us look up that entry. 0 to 1. J must be 1 and K must be X. And that is what we have over here. J1 is 1, K1 is X. And the same is true also about Q0. Q0 also goes from 0 to 1. So therefore we have J0 equal to 1 and K0 equal to X. And we can follow this procedure and complete the rest of the table. And that is what we will get. And you are definitely encouraged to do this yourself and verify that your entries are the same as what we have shown over here. Our final step is to obtain expressions for J0, K0, J1, K1 and so on. And we can obtain minimal expressions using the K maps that we constructed in the last slide, which are reproduced over here. For example, J0 is given by Q3, Q2 corresponding to this group here, plus Q3 bar, Q2 bar, Q1 bar corresponding to this group over here. Notice that we have two different types of X's here. The ones which are marked in the pink color came from states which are missing in the transition table, whereas these others came from our table for J and K given Qn and Qn plus 1. But they're all don't care conditions, and we can choose each one of them to be 0 or 1 so as to minimize the expression for J0 or K0, etc. In the map for J0, we have taken this X to be 0, 0, 0, 0, 0, 0. We have taken this X to be 1, 1, 1, 1, so that we get the largest possible groups containing all ones. Alright, now you can verify that all these other expressions are correct and they correspond to the maps given over here. So we have got K0 equal to Q3 bar, J1 equal to Q3 bar Q2 bar, K1 equal to Q0 bar, J2 equal to Q1, K2 equal to Q1 bar, J3 equal to Q2, and K3 equal to Q2 bar. We can now proceed to construct this counter with a circuit simulator and then simulate to check whether the counter does indeed follow the transition table that we set out to achieve. Let us now start constructing the schematic for the counter. First, let us get the components, and we will begin with the JK flip-flop. There is an element called JKFF1 pause for positive edge triggered flip-flop. That is the one. We then need to get AND gates. We can just get one right now and then copy it later. OR. We also need a clock element that will serve as our clock. Let us look at the properties of the JK flip-flop. It has got two real parameters. One is called delay high to low and the other one is called delay low to high. This parameter describes the delay involved when the output goes from high to low, and this one describes the delay involved when the output goes from low to high. Now these default values are 5 nanoseconds for each of them, and these are appropriate for our simulation because we're going to choose a clock period which is much larger than these values. So we will leave these properties at their default values. Similarly, the AND and OR gate also have these parameters, and they're both set to 5 nanoseconds, and we can leave those also at their default values. Let us look at the clock now. Clock has got two parameters, T1 and T2, which are relevant in this simulation. T1 is the interval for the first part of the clock in which it is 0. We will set that as 40 microseconds. And T2 is the interval in which the clock is high. We will set that as 10 microseconds. Apart from these elements, we will also find the connector element convenient. So let's bring that in. That is just a dummy element with no physical properties, and it can be used for wiring. Alright, our next step is to reproduce the flip-flop element 3 more times. So we do that by Control C, Control V, like that. Okay, let us now place the components and start our wiring, and let us get rid of this toolbox since we are not going to require any more components, and also the configuration panel. Okay. Alright, And let us copy this connector so that we can connect the clock to all of these. Now let us bring the clock over here and do that wiring. Since it's a synchronous counter, the clock must go to all these flip-flops like that. Next, let us look at the connections which are required. These are the connections that we figured out earlier, and you notice that many of these connections do not require any gates. For example, K1 is Q0 bar. Now this is our Q0, this is our Q1, Q2, Q3, this is our K1, and therefore Q0 bar can simply be connected to K directly like that. So it doesn't require a gate. The only gates we require are these for J0 and for J1. So we require one AND gate over there and some more gates over there. So let us figure that out now. Note that this Q3 bar, Q2 bar also appears in the expression for J0. That means what we have here is J1 ANDed with Q1 bar. So we have one AND gate there, one AND gate there, and one OR gate, and here we have one AND gate. So we require 3 AND gates and one OR gate. So let us copy this like that, and our J0 is going to be here. So maybe what we should do is to turn this around, because then this output can be directly connected to J0. What we will do now is we will place these gates and then we will start the wiring. So this OR gate gives us J0, and this one can be one of these AND operations. And this AND gate can be used for Q3 bar, Q2 bar. So in fact we can complete that wiring right away. This is our Q2 bar, and that is our Q3 bar. Like that. Let us use this gate to obtain Q3, Q2. Now this is our Q2, that is our Q3. So let us connect those two. That is Q2. And that is Q3. Like that. And the output of this gate should go to this OR gate, this one. Like that. One question that comes to mind is whether there is a crossover here or whether these wires are actually connected. The way to check that is to click on the wire, and that shows the complete path. So in this case, this wire is simply crossing over this other one. It is a good practice to use these connectors to indicate connections. So for example, if there was actually a connection over there, then we could have placed the connector over there and used that for our wiring. Let us complete the rest of the wiring now. The output of this gate must go to the OR gate like that. And what is this gate giving us? Right here, Q3 bar, Q2 bar ANDed with Q1 bar. Now this term is already here, that is J1, and we have already used one AND gate to give us that. So let us make that connection. And that needs to be ANDed with Q1 bar. This is our Q1 bar. So let us connect that to the other input like that. This is our J0. So let us connect that here. What about K0? K0 is the same as Q3 bar. This is Q3 bar. So we will connect that to K0. Like that. What about J1? J1 is Q3 bar, Q2 bar, which is this output here of the AND gate. What about K1? K1 is the same as Q0 bar. That is our Q0 bar. What about J2? Same as Q1. That is our Q1. That is J2. K2 is Q1 bar. J3 is Q2. That is our Q2. And K3 is Q2 bar. All right. So now our connections are complete, and we can move forward and name nodes and define output variables and so on. All right. So let us make this full screen and bring back our toolbox as well as the configuration panel like that. Okay, let us name the nodes first, starting with the clock. We can call this CLK. This is our Q0. So the Q of this flip-flop is Q0, and we will call this Q bar as Q0 bar. Similarly, that is our Q1, and that is Q1 bar, and so on. Let us now specify our output variables. And since we're going to select more than one, we can click on add variable with the control key pressed. And that allows selection of multiple output variables. So we will select the clock, Q0, Q1, Q2, and Q3, and we must remember to click on this add variable button once again so that the add variable mode is terminated. Okay, let us change these default output variable names to some meaningful names. All right, now we have completed the circuit editor part of the project, and now we will move on to the solve blocks. One important point, and that is we want our counter to start in the state 0, 0, 0, 0. That means we want the output of each of the flip-flops to be 0, and that can be controlled using something called startup simulation. And whether a flip-flop output would be 0 or 1 is determined by the startup parameter called QSV, and by default it is 0. So therefore, if we perform startup simulation with the default settings, our counter will automatically start in the state 0, 0, 0, 0. Alright, let us now proceed with the solve blocks. Okay, let us add a solve block and change its type to startup. That will set the initial conditions for the flip-flops. And now we will follow this up with a transient simulation solve block, like that. Now in digital circuits, this backward Euler method is not relevant. We can remove that. Similarly, this delta t, the simulation time step, is not relevant when we have digital simulation. So let us remove that as well. And we need to specify the end of the simulation time. Now our counter is a mod 9 counter, and one clock period is 50 microseconds. So we should simulate for at least 9 clock cycles, that is 450 microseconds. Let us say we simulate for a little more than that, 600 microseconds. We need to specify the initial solution or the method to obtain the initial solution, and that can be done using this statement here, initial solve. And instead of initialize, we should use the option previous here, because we want the output of this block to be used as the previous solution for the transient simulation block. Alright. Next, we want to add the output block. So let us add the output variables of interest, namely clock, Q0, Q1, Q2, Q3. Alright. And we are now ready to run the simulation. Okay. So now the simulation has been completed and this output file has been created. Let us choose time as the x-axis and let us look at all of these variables: clock, Q0, Q1, Q2, Q3. So that is the plot. This waveform here is the clock. This one is Q0. So clock, Q0, Q1, Q2, Q3. Let us now check whether our counter does follow the transition table which we intended to obtain. The first state is Q3, Q2, Q1, Q0 is 0, 0, 0, 0. That is Q3. So 0, 0, 0, 0. The next state is 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0. Then we have 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, and then back to 0, 0, 0, 0. So our counter seems to work as desired, and the design process is therefore validated. Alright. Now, as a small extension of this particular exercise, what you can do is design a mod 10 counter by adding one more state after, say, this state, and that state could be 1, 1, 1, 1, for example. So then you can go through this entire process of coming up with J0, K0, J1, K1, etc. and then simulate the circuit and check whether your design is correct. In summary, we started with a given state transition table and designed a synchronous counter which will satisfy the given sequence. We then made up the circuit schematic from scratch, simulated the counter, and verified that it follows the sequence we designed for. This is a simple circuit in terms of connections to be made, and therefore it's a good idea to try it out on a breadboard. That is all for now. See you next time.